Good afternoon, and welcome to today's webcast titled Water Quality Models 101, What Are These Things? This webcast is sponsored by EPA's Water Quality Modeling Workgroup. I'm Teresa Raffi with Tetra Tech, and I'll be moderating today's webcast. Thank you all for joining us today. First, I'm going to briefly summarize some of the features of today's webcast. If you have any problems viewing the webcast, you can type a question in the technical help box, which is located on the lower right of your screen. Please note that a conference number will not be provided for today's webcast. You must have a computer with the ability to play sound. A copy of today's presentation is available in the Downloads box to the right of your screen. Also, we encourage you to submit questions to the presenters using the Questions for Presenters box, which is found on the upper right side of your screen. This webcast will be archived for later viewing on EPA's Water Quality Modeling Workgroup page, and we will provide that link for you on a slide at the end of the webcast. Also, at the end of today's webcast, you will be able to obtain a certificate of attendance for participating, and we'll provide directions for downloading it at that time. The materials in this webcast have been reviewed by US EPA staff for technical accuracy. However, the views of the speakers are their own and do not necessarily reflect those of US EPA. Mention of commercial enterprises, products, or publications does not mean that US EPA endorses them. Now that we have completed the discussion of housekeeping items, let's kick off today's webcast. Our webcast today is the first in a series of 6 webcasts planned for the rest of the 2015 calendar year. All 6 of the planned webcasts will address various aspects of water quality modeling, and today's webcast will appropriately kick off the series by introducing basic modeling concepts. Our speakers have prepared materials that will explain the role of models in water quality investigations and introduce participants to such ideas as what types of models there are, things to consider during model selection, and what are the general model development steps and practical application issues. Our speakers today are Jason Gilday and Dr. Taimur Sheikh, and without further delay, let me briefly introduce them to you. Jason Gilday is a hydrologist in the EPA Region 8 TMDL program. He has 14 years of experience using water quality models to complete TMDLs and solve water quality problems throughout the U.S. Jason will be our first speaker today. Dr. Taimur Sheikh currently works for the Region 6 Water Quality Protection Division within EPA. He is a TMDL coordinator responsible for the state of Oklahoma. In addition to providing modeling support for NPDES and TMDL activities, he also provides modeling support related to the Western Outer Continental Shelf, Texas Territorial Seas, oil and gas permitting. Thank you, Jason and Taim, for joining us today. One final note before we kick off the presentations. We will try to answer as many questions as possible throughout this webcast, and we'll be asking questions of each speaker after their presentation. Due to the number of participants today, we have over 350 logged in at the moment. It may not be possible to answer all of your questions. We will be posting speakers' contact information on one of our final slides. And with that, we can begin our presentation. And I will now turn it over to Jason Gilday to start us off. Jason?
Thanks, Teresa, and welcome, everyone. We have had overwhelming turnout for this webinar series. I'm really excited that so many people opted to join us today. I think we had something like 1,300 people registered, so thanks. And I hope you get a lot out of this. And I'm going to start today's webinar with a little bit of history. You may be wondering, well, who are these guys and why are they giving this webinar now? We are essentially a group of TMDL staff at US EPA. We formed back in 2012 when a group of us just kind of got together and just wanted to kind of collaborate on what different projects we were working on and talk about modeling. We quickly expanded that group into standards folks and we let states join us. We started having a brown bag modeling series, and the group grew, and it's amazing that there are so many people out there doing some great work with water quality modeling across the U.S. Since 2012, we did some brainstorming about what could this group give back to the community, and we identified that we might be able to do a series of model trainings. At first we thought perhaps this would just be EPA-oriented, but I think it's going to be applicable to a wide audience. So from that, this webinar training series was kind of spawned, and we requested funding from EPA to conduct a series of 6 webinars. We formed a steering committee to figure that out. And on this next slide here, this was the steering committee represented by a group of people from various EPA regions. We got to doing some brainstorming about what kind of webinar series would help the most people. We actually put quite a bit of thought into this. There's a wide variety of model training options and a wide variety of you out there in the audience, people from having no modeling knowledge to some expert modelers out there. And we thought after some brainstorming that the target audience for this webinar series was going to be a water quality regulator who perhaps uses or reviews water quality models, but may not have a modeling background themselves. So from that, we were able to kind of devise this webinar series, and it really just kind of grew out of that idea from our target audience. And we came up with this purpose to develop a webinar series to help water quality professionals better understand water quality modeling and how models can be used to solve the problems facing water quality regulators. We developed a series of webinar goals, and sorry there's a lot of text on this page, but the goals were basically to have a webinar series that talked about basic modeling concepts. We wanted to provide an understanding of those concepts, provide some training on how to select, set up, and interpret a water quality model, provide guidance on how to effectively use and communicate your model results, provide training on water quality pollutants such as nutrients, metals, temperature, and sediment, and facilitate collaboration among water quality professionals who are using models. And I want to note here that there are, like I said, a lot of different modeling options that we could have, modeling training options that we could have done here. For example, there are trainings that focus on a specific model or specific pollutant and really get into the kind of the nitty-gritty of how those work. We felt that for this webinar series, that would be a little bit overkill or a little maybe too much training, and we thought we'd kind of back up and focus on these general concepts instead. So if you are kind of an expert water quality modeler, you're probably this is probably going to be a little basic to you. Conversely, if you have zero modeling experience, this webinar series I think is going to suit you well, or people anywhere in between as well. So our target audience for this webinar is essentially any water quality professional in any field, Clean Water Act regulators, people in the TMDL programs across the country, standards, wetlands, assessment, permitting, and then scientists, engineers, managers, students, attorneys, and we're making a basic assumption during the rest of this webinar series, and that's that you have a basic understanding of hydrology and water quality, maybe land use principles, things such as eutrophication and flow calculations, erosion processes, etc. And we're going to use phrases like that throughout. But this is a Modeling 101 class, so we really are going to start at the beginning with models and really explain from the beginning how those work and try to keep that more simple. But like I said, this is not a hydrology 101 class. So our webinar series topics, we arrived at 6 webinar series, partly out of funding and partly out of our brainstorming on what would make sense for the next few months. The first 3 webinars are kind of a group that go together. They'll build on one another, starting with this first one, Water Quality Models 101. The second one, in a month from now, is going to be developing and running a modeling project. And the third one, interpreting and using your model. For webinars number 4 through 5, we have some draft ideas of what we want to talk about for those, but we're also looking for some feedback from the group. So at the end of the presentation today, there's going to be a kind of a question and answer survey that asks folks on the line about what you would like to see for future webinars. So I've posed a question here: will I become a water quality modeler from this webinar series? And the answer is no, not from this course alone. Water quality modelers often have advanced degrees in engineering, hydrology, and programming. I think the point we want to make with this series is that you don't have to be a water quality modeler, though, to understand, interpret, and use a model. There are advanced modeling courses available if you would like to go that route. For example, if you want to learn how to use the model SWOT, there are week-long sessions developed by the people who have developed SWOT, and you can sign up for those, and likewise with some of the other models. And also, additional training may be offered by this group in the future, but for now we're sticking to these 6 webinars. So that's kind of the end of my intro materials, and I'm going to get into kind of the meat of the presentation now, starting with the question of what is a water quality model? And my first slide here, I have kind of the textbook definition of what's a water quality model, and that's a mathematical representation of pollutant fate, transport, and degradation within a watershed and or water body. So that's like I said, it's kind of the textbook definition. It's a little dry. You can see from the picture on the slide how some of those processes work, but I'm going to kind of break that definition down a little bit more in the next slide and talk about, maybe about what I just said, that textbook definition. What does that really mean? And so what we're talking about with the water quality model is an equation or a series of equations, and I've presented kind of a complex nitrate equation here for simulating nitrate. But it could be anything. It could be anything from a simple mixing zone equation to multiple equations combined together to simulate things like dissolved oxygen. Those equations then are developed by people who want to approximate an environmental condition. Somebody out there has a question, and that question might be, how can I mathematically simulate dissolved oxygen in my river or lake? And they've gone through the process of figuring out those equations and then putting that to a computer program to actually simulate that process. And then run by using a spreadsheet or computer program. So we're talking about a computer program that has some equations built in that simulates an environmental condition. And I think that's about the most basic definition that I can give you. I'll also note this is about the most complex math that you're going to see in this entire presentation. I know that people start to zone out when they see equations like this. We've kept it pretty simple, and again, this isn't a webinar series on how to develop a model. In other words, how to code it and how to write those equations. It's a webinar series on how to use your model and how to set it up. So I think this is one of the most important slides that I'd like people to take away from this series, and that's that a water quality model is a water quality tool. And when you're trying to solve a water quality problem, you've got a variety of tools in your toolbox to help you do that. And that may be things like an Excel spreadsheet, or it may be a statistics program, a GIS program. And your water quality modeling tool should also be in your toolbox. Like any tool, a model may or may not be the best tool for your project, and you really need to think about what tools do you have available and what tool is the right tool for your job. And so the real webinar purpose, the series purpose really, is to understand your modeling tools and know when and how to use them. And with that, I'm going to start talking about when and why you would choose water quality modeling. Water quality models are used for a variety of reasons, and again, this is one of those slides with a lot of text, but I'm going to get into some examples after this. The first in the list here talks about a model can be used to assess exposures to pollutants. You could use it to predict future conditions, support things like permits and trading options, extrapolate and interpolate values in times or places where observations are not available, assess the contributions of individual sources, or help make policy and management decisions. So your tool can be used for any of these reasons, but it's difficult to kind of visualize these in your head just with words on a page. So my next several slides in a row, I have some examples of how models have been used to display some results or help a water quality problem. With my first slide, I'm showing an example where a water quality model has been used to fill in some data gaps. And in this example, you can see that the month of January is presented for some kind of pollutant. And you've gone out there and you've sampled 5 different times, and those are the orange dots that you see. And you're feeling pretty good about how you've measured and monitored and represented this stream system. But you may have a question. Have I captured all of my peaks and troughs? Are there instances that are important to me that aren't captured by these 5 modeling points? And we, for example, ran this model for this month, and lo and behold, your monitoring data didn't actually capture all of the peaks and troughs. In fact, it maybe didn't even give you the right answer if you were looking at comparing these data to a water quality standard. So in this case, a model showed you, filled in the data gaps where data wasn't always available. In the next slide I have, we've used a model to characterize temporal variability. And you may have a situation where you're concerned about how does your pollutant change over time. In this sense, where we've shown E. coli data over a recreation season period. And as most people know, E. coli data can be highly variable. Taking just a handful of samples certainly isn't going to give you a great representation of what that variability looks like. And your water quality model can be used to characterize what that temporal variability might look like over time. In this next slide, we've used a water quality model to characterize spatial variability. So in this case, we have a river that's 38 miles long, and we've used a water quality model to show how temperature changes throughout the entire segment. You can see that temperature starts out a little lower at the headwaters at mile 38 and gets higher. And you would use the model for something like this if you're concerned about, where do my highest temperatures concern, how does my pollutant change throughout the river. And I've also have two lines on this particular graph that show a natural versus an existing condition. So you can use a model to run scenarios over that distance to characterize spatial variability over a number of different occasions or types of scenarios. In this slide, we've used a model to characterize the variability in depth in this particular water body. And at depth, DO changes with depth, and lakes can stratify. And you may be concerned about where does your low point of DO occur, or your question may be how does my DO change with depth? And it's really difficult to monitor, but it could be easy to model these situations and again run scenarios represented by these different lines. Models can also be used to quantify stressor and response relationships, and this has become pretty popular lately with the various nutrient standards packages going on and the various nutrient modeling going out across the United States, where a model can simulate the various processes starting from a nutrient being delivered to a stream, the processes that go on in that stream. In this case, we're showing nitrate and ammonia, and then how those processes interact with each other and within that particular water body. A model can be used to predict future conditions. You may have some questions about what is my water body going to look like in the future under some variety of scenarios. you could easily set your model up to show you what that might look like. And in this case, we've gone out to 2025 to show that this particular pollutant more than doubles over that time period. Your model can be used to quantify and compare sources, and this is one of my favorite graphs in that it really visually illustrates how the different sources are represented in your watershed and how they're contributing total nitrogen and total phosphorus. So it's very difficult to prove where your water quality loads are coming from without a model or quite a bit of monitoring data. And these kind of graphs are easy to build once you have a water quality model that's been developed for your water body. In my final scenario here, you can use a water quality model to run scenarios and evaluate BMPs. And you'll see on the pictures on the left that there's a river that was kind of denuded and didn't have any riparian vegetation or buffer zone. That is the exact same stream from basically the same vantage point below it. And you may be asking, well, what happens to my water quality once I've implemented these BMPs? And this is just an example that I've mocked up in this graph on this slide. But it shows that you can run a model to run various scenarios to find out how your BMPs would affect water quality. And in this case, we've used the model to show what kind of reductions would be needed to actually meet your criteria during the growing season. So still talking about why use models, I think you need to give some thought to model limitations and uncertainty. And the examples I've just presented are great examples of how a model can be used and how you can use your results to actually analyze what's going on in your water body. But the natural environment is complex and variable. And models are always constrained by computational limitations, assumptions, and knowledge gaps. Essentially, they're not truth generators. They're not magic boxes. They are able to simulate what you put into them. So models are best viewed as tools to help inform decisions, but scientific advances will never allow us to build a perfect model that accounts for every aspect of reality. That's just not feasible at this time. So models are not perfect, as I've talked about, but they are helpful. And I think this is another one of those key slides in this webinar series that they can help interpret past or current data. They help diagnose a problem. They provide an important line of evidence, and they provide an imperfect approximation of reality. And this is one of those famous modeling quotes that gets thrown around in a lot of modeling webinars by George E.P. Box, that all models are wrong, but some models are useful. So with that, I'm going to start talking about some of the different types of water quality models. And remember, this is kind of a generic overview in this webinar series. We could literally do a week-long or month-long or an entire course over a semester on water quality modeling or the different types of water quality models available. And they have those things available if you'd like to explore those options. But for today, we're going to keep it pretty simple and just talk about some of the basic overviews. So to start, I'm going to start with essentially two generic different types of water quality models. And the first one is an empirical or statistical model. And those kind of models are based on observed relationships. And you might be looking at this graph and thinking, well, that graph that you show there, that really isn't a model. That's just a line on a chart with some data. But you can use observed relationships like that and put some equations behind them and perhaps combine them with some other information that you know about your watershed to create something that is a model that uses that data to represent what's going on. And conversely, there are mechanistic or process-based models. And these are models that actually simulate the properties going on in the stream. In other words, there are equations that are describing how nitrogen and phosphorus or whatever your pollutant might be are actually working in the stream, as opposed to the empirical model where you're just using measured data. Moving on, kind of keeping this very general, you can think about water quality models as watershed models represented by the picture on the left, versus water body models, the picture on the right. A watershed model would be a model that's simulating the land processes going on within your watershed and how water and pollutants are being delivered to your stream. And obviously, if you're concerned about those kind of things, if you're going to select a model, you would choose something like that. And then alternatively, there are models that primarily focus on what's going on within the stream or lake itself. We can think of that as a water body model or a receiving water model. And those models focus on the actual in-stream processes and really don't have that upstream component. And two examples of these kind of generic types of models are, on the left is SWOT, and on the right is Qual2K. And I'm going to basically show a bunch of example models in the next few slides. They're going to be acronyms and names that might be a little foreign to you now, but there'll be some more explanation on those at the end in terms of resources to help you look those up. The next type of models I'd like to talk about are models developed for different water body types. There are some models that can be applied to any one of these water bodies. Other models are designed and run specifically for one type of water body. And those tend to be rivers or lakes or estuaries, oceans or coastal areas. I'll even throw groundwater in there. Each of those different types of models can be very different in how they're developed, but they can also be similar or they can be all lumped into one package. Models need to use spatial dimensions to make the complex world more simple, I think is the best way to put it. Rivers and lakes have very complex processes going on in them. They vary in terms of depth, they vary in terms of length and width. If you have a large lake or a large river, there's all kinds of currents, winds, various things that affect the processes going on in your model. And one way to simplify this is to kind of chop your water body up into different pieces, parts, whether that's chopping it up lengthwise from headwaters to the mouth, or chopping it up depth-wise, and maybe I should say if you're not chopping it up at all, that would be the 0D model shown here. Chopping it up lengthwise would be the 1D longitudinal model. If you're going to kind of vertically stratify it, that would be the 1D vertical. And then you start getting more complex. You can chop it up length and width, 2D. You can chop it up length and depth, 2D laterally averaged. Or you can get into a full 3D model that actually looks at the water body in a full 3D perspective. The next graph also illustrates the same thing, but in kind of a different way, showing that the different spatial dimensions, like I just talked about, can be displayed differently. It's not always visually intuitive with that previous graph. So we created this one to just kind of give you a different perspective of how your model would actually see your water body with spatial dimensions in it. Models can vary in terms of what time step they're run at, and we tend to think of these in two different ways. We tend to think of the first type as a steady state model, which if you look at the stopwatch on the right there, we're stop watching the water body. It's a snapshot in time. A steady state model has constant inputs and outputs, and there may be instances where you would have a problem that could be solved with a model like this. And something like a mass balance or a Qual2K model would be doing that. Versus a dynamic model, which has time-varying inputs and variable inputs and outputs. In other words, we're not putting a stopwatch to that time period, but as the graph shows, we've got multiple inputs over multiple days. And these tend to be some of the more complex models like HSPF, EFDC, or WASP. So I've talked about all the various models that we just presented. Kind of, I guess, another type of model is one that's linked together, where you can, perhaps you're interested in what's going on within your watershed and the processes going on within your stream, and perhaps even groundwater, and perhaps even other things such as atmosphere or climate modeling. You could link all of these together to develop some really complex models. Not all of our water quality problems certainly need all of this, but it's doable, and it can create for a very robust, comprehensive model at the end of the day. Other types of water quality models have other factors that define them. Some models are built for different time steps. There are models that are meant to be run to look at yearly data and yearly loads versus models that can look at simulations down to the hour, minute, or second process. Models can be developed for different sources. There are models that are built just for urban sources and urban areas. Versus there are models that are built to simulate the practices going on in agricultural lands or forest or wetlands. There's different pollutants. Models are developed for different pollutants. Many of them will simulate more than one pollutant, but some of them are pollutant specific. Models are developed at different scales. You may have heard of something called a field scale model, which is maybe you're looking at an acre or a small field implementation project versus a model that's looking at something like an entire watershed or perhaps even the entire United States or entire Mississippi River Basin. And then finally, their models can be kind of stratified into models that are in the public domain. They're developed publicly, or they're developed and distributed for free, versus models that are developed in the private domain, which you might have to pay a license fee to use them. So some of the commonly used models in the world that water quality professionals tend to work in are things like Bathtub and Qual2K and the entire list of models you have here. I don't feel that I need to run through all of these. The point of this slide is really that there are a lot of different types of models in the world. They do a lot of different things. They all incorporate all of the different factors that I've just talked about. And when you are selecting your model, you need to know what your model does. Well, I guess first you would need to know what is your water quality modeling problem, what kind of answers are you trying, or what kind of problems are you trying to solve, and what kind of answers do you need. And then using that, you would go look up the different types of models and say, okay, perhaps that step L might be the model that I need based on the water quality problems that I'm looking at. I should say this is the end of my part of the presentation, kind of this overview of all this. Tame is going to be talking about how do you actually select some of these water quality models and go about identifying which ones you would use for what kind of project in the second half of the webinar. So if you are submitting questions right now related to how selecting one of these or how do I know when to use that, that's coming up in the next few slides. But we're going to pause here now and take questions for my half of the presentation.
Thank you, Jason, for that really good overview of both the modeling series and then that really awesome introduction to what are water quality models in the first place. And we do have a few minutes to take a couple questions. And the first one that I got is actually from someone who wants to know, how could someone join the water quality modeling work group that you were talking about in your introduction?
Yeah, that's a great question. Thanks. Like I said, it's been kind of a grassroots effort so far. It really has been just through emails and word of mouth. I think once we're done with this webinar series, I'll try and put together more of a formal group. Really what we got to do is we got to be having kind of monthly or bi-monthly phone calls where we would do kind of brown bags, have people present, and just generally discuss some of the modeling issues out there. And I think it would be great to have other people join in on those discussions and even volunteer to present. So for now, that group is kind of on hold, like I said, because of the webinar series. But once this wraps up, I think perhaps the email list of participants we get from this would be a great way to reach out to everyone and kind of reform that group and think about how we can make it better.
Great, thank you. Another question is, what is BASIN and what is it used for?
Yeah, good question. BASIN is actually a compendium of models. It was developed basically to assist a user who perhaps, again, isn't an expert water quality modeler themselves. It will compile data. It will help you kind of in that model decision process. And so it doesn't really fall into the different categories of models that I just described. Because it is, in fact, this compendium of a whole bunch of models and a whole bunch of, I guess, processes and front-end GIS tools and things like that to help you with water quality modeling. And that, by the way, that is an EPA-supported model, still ongoing with the Office of Research and Development, and I would encourage people to look that up.
All right, thank you. And I have another question here about CorMix. We don't see CorMix listed in the list that you provided. Are there particular models that EPA likes to use, prefers to see?
No, there are not particular models, and that's something I really want to stress here with this webinar. EPA does not endorse models. I certainly do not endorse models. What tends to happen is that as you are progressing through your professional career, you get to know a handful of models through using them for various projects, and sometimes those tend to be the models that you tend to specialize in and then therefore use in the projects. For me, CorMix isn't a model that I've particularly used for the water quality model, problems I've encountered in the past, but I know that a lot of people do use it. And so I think one of the big take-homes today is that there are more models out there than I could possibly list on here. It's probably in the hundreds, if not thousands. And there's a model just about anything you can think of. And it's maybe a little daunting to pick which model you would use, but Team's going to talk a little bit about some of the resources that can help you choose that, and how to proceed with formally selecting the model for your project.
Great. Here's one about, I guess, linking models, and maybe this is better for later in the presentation, but does running a sequence of models make results less reliable?
That's a difficult question to answer. No, I think the answer is no. Every model has uncertainty built into it. And you really need to think about what kind of questions you're asking and think about what kind of uncertainty you are willing to live with in your results. A model that isn't linked may have more uncertainty than a model that is linked. It really does rely on what you're trying to do and what kind of results you're looking to get.
Okay, I think we have maybe time for two more. So how about another one about, is it possible to download or obtain free modeling programs from EPA?
First of all, EPA tends to not develop models, although we have helped develop a few in the past. So we do have a website that Tane's going to talk about later that has a list of models. Maybe it's a little cart before the horse here. Tane's going to cover in a number of slides at the end some public websites and public documents that are available for downloading different models, figuring out what a model does. There have been a number of compendiums done over the years to kind of just summarize, okay, SWOT does this, and Qual-K does that, and CorMix does this. Those are going to be discussed a little bit at the end, and so that will be coming up.
Are there, one last question here, I think, and then I think it'll be time to move on. Someone is asking about model-specific training. Not so much the theory behind a model, but actually applying, building, setting up, and using the model. Are there plans to provide training?
So there are trainings available already, available to anyone nationwide for a number of models. The ones that come to the top of my head are SWOT and WASP. I think CE-Qual W2 offers a training. So if you know of a specific model or type of model that you'd like to get additional training on, there are resources available. Now, that being said, kind of depending on where this group heads in the future, it's possible that we may be able to do some of these more specific kind of trainings. But I think for now, EPA doesn't, well, I guess WASP is an EPA-offered training. But for now, EPA doesn't tend to ourselves have a bunch of model trainings available.
Okay, thanks. And actually, one more question before we
Sure.
move on to the next section, which I think is a good way to wrap up. The first section is whether or not there are any books, textbooks, websites, etc., that you would recommend as a good introduction to water quality models.
Yeah, there are, although with the caveat that EPA does not endorse products, of course. There's some of the standard classic textbooks. Steve Chapra's textbook comes to mind. The Tillman and Mueller water quality modeling textbook comes to mind, that are used, kind of regularly in universities as kind of the generic, all-encompassing water quality surface water modeling textbooks. There's also, again, a number of websites out there that you could just go into Google and type in water quality modeling training or whatnot and find resources for those kind of things. And then finally, Tane is going to show you some of those websites and resources at the end of the presentation.
All right, thanks, Jason. I think we can move the process along now, and I'm going to turn it over to our next speaker, Dr. Taimur Sheikh. He's going to go into a little more detail about types of models, what goes into model selection, and application basics. So, Taim, it's all yours.
Thank you, Teresa. And Jason, thanks. So I have the honor of talking with you guys about choosing a water quality model. And it really doesn't have to be eeny, meeny, miny, mo. It can be, but that's not necessarily the best way to go. But there are lots of things to consider. And kind of as, on the front end, we tend to gravitate to what we already know. And with that in mind, we tend to make decisions based on our comfort level. That doesn't necessarily mean that we always get the best model for the problem we're trying to address. And so I want to take a few minutes and really discuss the model selection process. Probably what gets the cart before the horse every time, at least initially, is that we tend to start off with an idea of what we need, but really it's kind of undefined. Let's say we know there's a problem in a water body, and we think it's, let's say it's pathogens. And we can jump straight ahead to, oh, well, we can use this model, or we can maybe apply this particular methodology. I would want to start off by saying, caution is a good thing. First things first, and Jason already started to hit on it a minute ago, we need to really define the decision that we need to make, and then what information do we need to make that decision well? What information do we need to formulate a model that will represent the reality we're going for? So when it comes to, let's say, management decisions, we're talking about what are the standards that are in play? Are there particular pollutant loads that we need to be able to hit? Pollutant concentrations, and then also are there secondary impacts? Maybe there's an ecological impact that we need to take into account, as well as a concentration limit, for example. So that's probably the very first thing when we start thinking about water quality modeling. What question are we trying to answer? And and dovetailing right into that is, all right, so we have a question. Is there a critical condition, or do we need a continuous simulation? And that usually is directly informed by the standard. So if you're familiar with TMDLs, or if you're even a little familiar with water quality modeling, the idea of a critical condition or a steady-state model versus a continuous simulation, as soon as you know what you're trying to hit in terms of a standard or in terms of a target, that informs that question right off the bat. And once we have it in place, we really need to consider the water body and its surroundings. So when we talk about identifying the land, water management features, what kind of water body are we talking about? A lake, a river, an estuary? Are we talking about, let's say, the ocean, Gulf of Mexico? We need to kind of define the area that we're interested in. And then really think about what does the watershed look like. So are we talking about a rural watershed? Is it an urban setting? Is it a forested setting? What are the characteristics of that area that are really going to drive the modeling decisions that need to be made? As we've touched on briefly already, spatial and temporal resolution. Are we concerned with the area itself, or is it really just the water body, and are we focused on one particular point in time, or are we thinking that we need to begin with, let's say, a 5-year or 10-year period? And really, the type of pollutant often informs the temporal resolution that we need. And so there's usually a very firm connection there between the two. Also, I should mention management techniques. Are we dealing with stormwater, or is flow managed, whether through, let's say, a lock and dam system or some other flow management system that exists? So after we identify the land and water management features, we move on to, well, are there any special things we need to be thinking about, any special processes that may not be kind of common to our usual model set? An example would be linking either an organism or an ecological response to an in-stream concentration. That might be something that we don't normally run into, but it does happen. Another example would be trying to link, let's say, air deposition, and then of course the land use and the area upon which that pollutant deposits, and then its runoff into a stream or river, and its eventual in-stream concentration. And from there, we'll talk about the practical issues that then occur. Let's see. Unfortunately, or I guess fortunately, depending on how we look at it, at the end of the day, the practical defines what we can and can't do. Like I mentioned earlier, we tend to use what's available to us, and lots of times, what features are available takes a backseat to the resources that we have at hand. In some ways, when it comes to model selection, it helps to actually start with a clean slate and not to already have a particular idea or viewpoint that you're shooting for. But some of the features that come to mind when it comes to the practical issues, is the model you're thinking about, or the models you're thinking about, are they easy to use? Are they available? Credibility is really important. Have the models that you're considering been demonstrated to address the problem that you're looking at well? Is there a history there of succeeding in representing reality? And of course, there's also just our own personal preferences. Are we trained to run that model, or do we have trained staff available? Also, and this is a big one, do we have the available data necessary to run a given model? And with that, do we have the time necessary to make that happen? The question of data, and I think for our next webinar we'll talk about that more, but the question of data really drives model selection, and we tend to sometimes breeze right past that, but having the right kind of information to drive your model set is absolutely vital. And then once we've considered all of these things and we've gone through the process, and maybe we've gotten down to a short list of models, we evaluate the options, and then we select what will hopefully be the most representative model for the problem at hand. So with that, let's kind of unpack some of the criteria for the model selection process. And I'll go through simple and complex, and I'll briefly touch on a few other items and kind of go from there. Okay, so in thinking about simple versus complex models, I realize a lot of us may not have a good frame of reference for what those terms really mean and what might be indicated there. But you can think of it in terms of simple as, how much experience is necessary and also how much data is necessary. So when you want to choose a simple model, or when would you want to choose a simple model? Well, if you have a few sources, or maybe one source, maybe if it's just 2 or 3 point sources involved, a couple of publicly owned treatment works, for example, that might lead you to think, okay, I can use a simple model. When you're not concerned about the pollutant speciation, if the in-stream chemistry of your pollutant is not as important, whether that's oxidation state or deposition or whatever it happens to be, if it's something that exists essentially neutrally in the water column, maybe a simple model is the way to go here. Also, if you can get by with steady state conditions, if you don't have to have something that varies in time, again, a more simple model may work. And then, of course, a big one, having simple hydrology. And an example of that would be just kind of a free-flowing stream. There's kind of as a uniform flow, that kind of situation. But so we need to consider a more complex model. Well, when we have multiple sources involved, and especially if those sources are somewhat divergent in nature, and they have fluctuating discharges, or if you have really 2 totally different types or kinds of discharge involved, you might want to consider a more complex model that can represent those sources. Also, if you have a more complex pollutant, being able to represent the chemistry involved can be really important there. So, as I mentioned, the opposite of having a really simple water body, if you have something that's stratified, if you have, let's say, a deep lake or for that matter, even a deep river, can be stratified and can have more complex hydrology associated with it. So, really, the harder it gets to represent the movement of water and the uniformity with which the water is being treated in all dimensions, that kind of pushes you more towards a complex model. All right. And then let me just briefly touch on spatial dimensions. Jason already hit on a few of these items, but I'll probably give you a little more detail. So when is a one-dimensional water quality model appropriate? Well, in terms of one dimension, if there's very little lateral variability in the water, or there's no stratification, or if there are no dead circulation zones, or really if it functions, and you may have seen this before or heard of it before, but if it's essentially like a continuously mixed batch reactor, if you can imagine a bucket that's just constantly being mixed, if the water is uniform and the concentrations in the water are uniform, that's a good time to be thinking about a one-dimensional model if that's your hydrology, and if that's really kind of the world in which we are working. And I've mentioned an example, that would be a well-mixed river or stream. And then when would you consider a two-dimensional water quality model? Well, if you have lateral variability or vertical stratification across a water body, you may want to consider a 2D water quality model. The second bullet there, having complex horizontal circulation patterns, really kind of gets to the point of if your water body does not behave uniformly, you have to up the dimensions. So if certain parts of your river or lake just do not behave the same way as the rest of your water body, then it's no longer representative to go with a 1D model. You need to consider a 2D or maybe even a 3D. An example for a 2D model would be using, or would be applying it to a shallow, well-mixed lake or an estuary. And then what about 3D models? And before I even say anything else, when you start talking about 3D models, your data requirements just go way up. So before you even start considering one, just word to the wise, make sure you have the data available. So when would you need to apply one? As kind of a combination of the last two slides, when you have variability across your water body laterally or in the horizontal, if you have a vertical stratification, and really if you start seeing complex circulations. So if there's something in your water body that, let's say you have a situation where you have eddy currents that are forming, or you have essentially pollutant hotspots that form because of those eddy currents, it's really time to start thinking about a three-dimensional model. And as I mentioned earlier, you can apply one when you have enough data to be able to calibrate that kind of a model. It does have a significant data demand, but if you do have it, the benefits are really quite impressive. So something to think about as well. And an example of where to apply a three-dimensional model could be a deep reservoir or lake, or maybe you have a poorly mixed estuary. That would be another place where that might apply. So with that, let's touch on when to use a watershed or receiving water model. So when would you use a watershed model? Well, before we even get into that with too much detail, one thing about watershed models that folks kind of need to know. In a watershed model, all sources, whether point sources or non-point sources, at the end of the day are essentially treated as non-point source loads. What that means is when you have your watershed and it's subdivided into its sub-watersheds or sub-basins, all of your loading really is combined at the edge or at the end of that sub-basin. So whether you have it in a watershed model as a point source or a non-point source, when it gets carried through to the next sub-basin, it's all getting lumped together as a non-point source load, and so moves through your system. That doesn't mean that you can't have point sources in a watershed model. It just means that as your information travels through that kind of a system, it gets lumped together as part of the non-point contribution. But so what makes kind of a watershed model a watershed model? Well, most of these are or rely on what's known as a hydrologic response unit, and that's an area of space, let's say a patch of land that has similar precipitation, land use, impervious area slope, drainage type. Essentially, it has similar or the same physical parameters and receives similar or the same inputs to the system. So when you're using a watershed model, or when you should use a watershed model, is when you're looking at a larger area and the transport of pollutants or whatever it is you're interested in, the transport across a wide area, and you have non-point sources and non-point source contributions involved. So what about a receiving water model? And I think somebody mentioned Cormix earlier in a question, so that graphic was actually taken from a Cormix model I ran a couple weeks ago. So yes, we do use it. So when would you select a receiving water model? When you're interested in the fate of the pollutants involved, where do they end up? And you want to simulate really the state of a given water quality variable, whether that's a concentration of dissolved oxygen in the water column at a certain time and distance, or whether that's the concentration of an effluent at the edge of a mixing zone, whatever it happens to be. When you want to know about that particular species at a given time and place, that's when you really want to look at a receiving water model. Another way of saying receiving water model is water quality model. And I should mention probably at this point that a lot of the models we use are incorporate both kind of the hydraulics of a model, or the hydrology of a model, as well as the water quality portion of a model. Lots of models fuse these things together, and so you may have a model that has both the ability to handle the hydraulics or the hydrodynamics involved, as well as the water quality. They're not necessarily mutually exclusive. Several models actually incorporate them together. But back to receiving water models. A receiving water model really incorporates kind of the chemical and the physical and the biological processes that get you to that concentration that you're interested in or that load you're interested in. And they're driven, those types of models are driven by input from things like hydrologic models where you get the hydrodynamic data, or if you have external point and non-point source loadings, those will drive the water quality. Also, for a water quality model, there's these things called forcing functions. And really what that does, a forcing function tells the model this is the condition that it is. This is the condition that exists. It forces for lack of a better way of saying it, it forces a certain handling of that input in the system. So, for example, temperature is a forcing function, or pH can be a forcing function. If you know what the temperature is and you put that into, let's say, a qual model, the qual model will, force that temperature in that system. All right, so some examples. And I have 3 examples that kind of go through, kind of very simply through the idea of selecting a model. And at one point, I believe these things were animated, but they're not now. So if you look at the slide, you'll probably see the answer to the question that's being posed. That's okay. We'll just do that. So with that in mind, let's go to example situation 1. So kind of just think with me, if you would. If you have a pollutant, let's say nutrients, and you know that you're wanting to evaluate nutrients at a critical low flow. You also know that your predominant source is a point source, and you're dealing with a river. Oh, and on top of that, there's a DO standard of 5 milligram per liter at the 7Q10. Given all that information, what do we need to be able to do? Well, since we're dealing with a low flow condition, that kind of informs the idea that, well, we can probably get away with a steady state model. So we don't have to have something dynamic. Also, since we're dealing primarily with a point source, and I haven't mentioned non-point sources at all, we may not need a watershed model for this problem. We may be able to get away with just a water quality model. So with that, and knowing those parameters, a suggestion would be to use something like Qual 2K or one of the standard Qual models that's out there. So with that, what would the data needs be for running a model like that? Well, anytime you think of a Qual model, knowing something about the cross-section of the water body, the longitudinal slope of the water body, the surface roughness at the bottom of the water body, all of that information informs mixing and informs the movement of water. Of course, we need some monitoring data to be able to do that. We'd want to characterize kind of the background conditions. So what is the water quality like before we get to our point source? And we'd have to have some data to be able to calibrate the model kinetics Really that means make sure that the way the water is being handled in the model is a realistic approximation of what's going on. And I know there'll be more discussion on calibration in next month's webinar. Also, we need some information on the source discharges. We'd have to characterize the effluent and know something about that. For example, what kind of load do we have? How much water is being discharged? And kind of lastly, we have to have a feel for any tributary inflows or any other sources of water to the system. And those are all bits of data that you would need for like a Qual 2K model. Well, so here's example 2. What if we have a situation where we have, let's say, a bacteria, let's say we have E. coli, and a problem shows up in mid to high flows. On top of that, the predominant source is both point source and non-point source. We're dealing with a river, and the target we're looking for is 126 CFU per 100 mil. Oh, and by the way, we have a frequency of violations, once every 3 years. So we can see that the target we're trying to hit is being exceeded. Excuse me. Well, since we know we have both point and non-point source contributions, and non-point source is definitely part of the predominant source, we may want to consider something that can simulate an area, and simulate a watershed. And since we're also dealing with mid to high flows, that would seem to indicate that weather is a part of the issue. And so we may want to consider something that's continuous, something that's over an area and can handle wet weather conditions. And so kind of going through that line of reasoning, I think we would end up with something like HSPF or LSPC or SWIM. And yeah, I realize that's alphabet soup right now, but I think as you just dig on what kind of models are out there, I think you'll start seeing certain acronyms just come up more and more frequently. But so, yeah, that would lead me to essentially a watershed model. So what are the data needs for those? Well, if we're talking watershed, it means we have to have landscape data and stream data. We need to know the land uses involved, the soils involved, the streams involved, whether or not the E. coli are from animal wastes or not, have some way of quantifying that information. And these types of models can get pretty data intensive as well. For example, for land use, we could use the National Land Use, the National Land Cover Database, housed by USGS, or there are several databases out there that we could incorporate to get information to build our watershed model. Also, we would need some land use monitoring to be able to calibrate the model, and we need to establish a baseline condition. Essentially, what are the conditions when really nothing else is going on? What is kind of the current, given no other inputs, what is the current state of the water? Of course, we would need some in-stream monitoring to be able to calibrate the model as well. And of course, for those point sources, we would again have to characterize the effluent. And probably the thing to point out here is you can do a watershed model without too much data and a whole lot of time investment, but it really comes down to what are you comfortable with in terms of of how well your model represents reality. And really the level of effort that you put into a watershed model like HSPF or LSPC really is dictated by what level of detail are you trying to get to. How well does the model have to represent reality? Are you okay with, let's say, a 10% error on a given day? Or do you have to have something more like a 2% error, which, talk about getting pretty tight on errors. But that kind of information really informs how far you have to go. So as you think about the process of modeling, having in the back of your mind what's good enough is an important question to really kind of maintain and have that readily available for you. All right, so my last example, and just, here's my preemptive warning. This is kind of a red herring. Let's say we have bacteria, and we have a critical flow of a 7Q10. We have one point source involved. It's a river, and the criteria is 126 CFU. So what model would we need to use? And there it is. Wait, you may not have to model. The point that I'm trying to get across here is we don't always have to model. We may be able to just apply criteria and a pipe if it's a permitting situation, and that's good enough. Not every question has to have a model. Lots do. There are lots of times when we have no other choice. The model is the best approximation of reality that we can get our hands on. But there are those situations when, well, there may be an easier answer. And those are few and far between, but they do exist. So with that, let's talk about resources for a minute. And I'm going to probably kind of cut in and out from the presentation to my own desktop and back, so just kind of bear with me if you would. But there are several resources available. Let's see, so WRF actually has the select tool, which helps with BMPs and really BMP selection. The Modeling Technical Support Center, I believe at least their web page still exists, and I think the primary contact for that is Tim Wool out of Region 4. And I'll hit on some of these web pages here in a second. Also, somebody mentioned Basins earlier. Basins has a pretty decent web page that kind of walks you through its system and process, as well as the CREM knowledge base that exists, which has a registry of EPA applications, models, and databases called READ. I should mention, CREM doesn't really exist anymore. It's actually now essentially EPA's modeling community of practice. But we'll get to that here in just a second. So let me stop sharing the presentation and go to some of these pages. So there we go. Okay. So hopefully everybody can see that I've made the switch to the CREM web page, which is the Council for Regulatory and Environmental Modeling, which of course, as I mentioned, no longer exists as such. But the CREM page, it's still out there, and it has a lot of information on what models are available, and its knowledge base is pretty solid. There's a lot of information about what kind of models are there. They've been evaluated for kind of the different applications that exist, and it gets to more of a. I dare not click on this because I don't want to free up my laptop, but it gets to more of a description of what each model is, what it does, and really what are its strengths. I mentioned the WRF select tool. Let's see. And that page is listed on the presentation as well. And as I mentioned earlier, it's primarily BMPs and LID practices. And so that may be helpful for situations where, let's say BMPs are the appropriate route. Let me take a little bit of time and move over to basins very quickly. The basins page, as Jason mentioned earlier, it really is kind of this, kind of overarching interface into multiple models with multiple data tools involved. Basins is a great tool, not just for running HSPF, which is built in, or any of the other built-ins that are in Basins. It's really a great tool for just data mining, getting the information that you probably are going to need to run a model. I mean, you can do this in ArcGIS as well, but if you want to delineate your watershed, it works really well for that. So I would suggest, even if you're not sure what model you need right off the bat, if you need to do some data mining, Basins isn't a bad place to start. It actually has access to a lot of good information. So I would kind of definitely put a plug in for that. And then, I don't think I've gotten to this yet, but here we go. There's also several white papers that exist. And here, let me see if I can get to there. And the reference is on the presentation. When we get back to it, you'll be able to see it. But there are several white papers that evaluate models and really kind of evaluate, how well do they work in any given application. And one thing I want to just kind of scroll through with you is kind of the applicability of each of these models. There we go. Hopefully you guys can follow this. Since I can't hear anything, if you're there cursing, I have no idea. But hopefully you can follow along with this. So this particular white paper provides a list of, I think Jason was right, hundreds of models and where they apply. And just I'll pick one. Let's say CE Qual W2 applies in both river, lake, reservoir, tidal estuary, and coastal scenarios. This kind of information can be really helpful, especially if you're not used to going and digging into what model is going to work best for me. It's nice to have a resource like this to be able to go to and say, all right, I know I've got a tidally influenced water. What works well in that situation? And you can already get maybe a shorter list than you would have to start with. So I would definitely recommend using it as a resource. I will say it's a little dated. I think the document came out in 2005. Here, let me back out of this. I'm going to stop sharing my page. Okay, and we're back to the presentation. I would definitely recommend taking a look at that, and that's on the next slide. The link is there. I know you can't click on it and get to it right now, but if you download the presentation, you can just copy and paste it. The TMDL Model Evaluation and Research Needs document is a really helpful resource. So again, recommend that. Oh, and I didn't show you this, but this exists in there as well. The model selection resource also has a series of fact sheets for each model and includes contact information. As I mentioned, the document was completed in 2005, so it's a little outdated, but it gives you a good starting point if there's a particular model you're interested in. Okay. So with that, let me just kind of summarize what we've hit and go from there. So what have we learned? Well, hopefully, we've learned a little bit about how to define a water quality model. We've got a better handle on the types of models that exist. At least, now we've heard the general terms. We have a little bit of an idea how to select a model and go through that process. And we've seen some uses and examples of different models in play. So with that, let me hit the take-home. As we started off, you don't have to have a modeling degree to be able to understand and use a model. It doesn't hurt, but you don't have to have one. In fact, most of the people I know don't have modeling degrees. Another take-home is really that you can be confident in using models to address water quality issues, and know that there is a community that, as Jason mentioned, kind of this grassroots community that exists and continues to expand, that's here to help. One of the things that a lot of us that are involved in the national work group are involved because for us it's an interest. We would be interested whether we were modelers or not. It's just something that we kind of gravitate towards. So please feel free to rely on us if you have questions. We may not have all the answers, but we're definitely willing to help. And also, water quality modeling, really is an effective tool in making that connection between the cause of, let's say, a water quality impairment or an issue, and then the effect that's seen out in the environment. So I hope that that's been informative. In about a month, we will have our next webinar, in which we'll be discussing kind of more model setup, CLOPS, calibration, a term I've already hit on a couple times, but that'll get a lot more explanation, and of course model acceptance. So with that, I believe it's time for questions.
Thank you, Tame. That was a great presentation. Provided a lot more in-depth detail to the subject matter that Jason sort of touched on the tip of the iceberg with. And I think we have plenty of time now for a lot of questions, and we've been getting some really good ones from the audience. I want to remind everybody, I know some people have been having difficulties hearing the audio, and this entire webinar is being recorded and will be archived and placed on the TMDL Workgroup webpage in about 2 to 3 weeks after the conclusion of today's webcast. So if anyone has had a hard time hearing or following along today, we do apologize, but we will be recording and making that archive available to you so that you can listen to it at another time. And hopefully we will have time to get to almost all of the questions. If not, we should also be able to contact the speakers, and you should be seeing their contact information on the slide that is showing right now. So with that, I wanted to go ahead and sort of start asking questions of both Jason and Tame. And the first one is from someone who has heard of water quality models described as distributed versus lumped. Can either of you explain the difference? Tame, you want to take that one?
Sorry, I was on mute. I apologize. Okay, so yeah, a distributed model versus a lumped parameter model. Really, you can think of it as a way of handling the parameters themselves. And I know there's probably a better way to describe this that I just can't think of, but to use something like, what would be a good way of describing it? Something like maybe like a watershed model is probably a good example of a lumped parameter model. That all of your parameters are really, I guess, associated with that particular area, that particular HRU, for lack of a better way of putting it. And so that group of parameters moves through your calculational system. Whereas if it's distributed, you can think of it more as kind of averaging across, how would I put that? If you're talking, let's say, a segmented river, you're averaging across that information for your calculation. And I know that doesn't, it's not probably the best way to describe it, but that's what comes to mind.
All right, thank you. Another question, and this has to do, kind of gets to what you were talking about, Team, earlier about the community, the modeling community that is out there, and whether or not EPA has ever considered creating a web forum for discussion around modeling. Jason, you want to, or Team?
I would say, Jason, you want to, or shall I take it?
Go ahead, Tim.
As far as I'm aware, there has been some discussion as having, or putting together a forum for kind of general modeling discussion. And in a way, I think what CREM has become, the kind of the environmental modeling community of practice. I think that's kind of taken a little bit of that role. But in terms of, like, let's say, just kind of a web-based forum that exists out there in the ether, it's been brought up more than once. And I think if there's a continual clamor for it, if there's external interest, it very well may become something worthwhile. The thing about modeling is it kind of comes in waves. We get a lot of interest, and then the interest tends to wane when some other problem comes up, and then, oh no, we need to be better at modeling again, and we kind of come back to it. So I guess I would say to that, the squeaky wheel does get the grease.
As always, yes, it does. Thank you. How about this question about whether or not modeling could be used to assess or how modeling could be used to assess the effectiveness of a 319 funded restoration project? So, watershed restoration projects, BMPs, how could you use modeling to evaluate the effectiveness of that?
Well, so a few things come to mind there. For lots of 319 projects, there's modeling already associated with the BMPs that are intended to be implemented. And normally, the effectiveness is really reached through going out there and then monitoring after the implementation of the BMP over a given period of time. But as was discussed earlier, I think rarely, if ever, do we see 24-hour continuous monitoring being put in place after the BMPs are situated. So having the data, let's say having monitoring data at a representative interval, whether it's monthly or even monthly or biweekly, whatever that happens to be, may be a way to then use the model that was used to develop the 319 plan and really kind of augment it with the data that exists now. So, with the reduction that hopefully has occurred, does the data we see now match with what we expect to see with the reductions we planned?
Okay, thank you. Does Jason, do you want to have anything to add to that?
I was just going to add something else, and it's one of the themes that I was trying to harp on, and that's, certainly models have been used with 319 projects in the past, but it comes down to picking the right model for the right project. And for example, if you have a 2-acre 319 project that you're trying to evaluate the effectiveness for that project, you certainly wouldn't want to use a model designed to give you results at the Mississippi Scale River Basin. It comes back to there are field scale models for small spatial models versus models designed for large scales. And so for any project, 319 or other, the first step you should be asking is, what is the scale? What are my pollutants? What am I looking at? And then use those questions to pick the right modeling tool, if you even need a modeling tool.
All right, thank you. Another question. You guys may or may not be able to answer this, but it does harken back to a slide that Kame showed earlier about what is the status of basins, and will it be updated?
Mm-hmm. Well, so basins is still being, for lack of a better term, it's still being managed, and it is being updated, though very slowly. I believe that it's been housed by different groups. At one point it was ORD, and I think Region 4 got it back again for a little bit. And it's kind of made the rounds. But as far as I'm aware, there is at least some impetus for maintaining basins. And really what I mean by that is when the links to the GIS data break, reestablishing those when there's new GIS data, and updating the links to the pertinent databases to be able to pull DMR information and that sort of thing. So as far as I'm aware, those updates, will still occur. I wouldn't expect to see, major changes to the system anytime soon, though.
Okay, great. Thank you. Here's another question about when will the WASP 7 manual be out? Do you guys know? Tame or Jason?
When will it be out? That's actually probably the person that will answer that with the most clarity would be Tim Wool, who I don't think is on this call. But that question really should be directed to Tim Wool at Region 4.
All right, so it sounds like there's interest in Tim Wool at Region 4. Thank you. How about another question here? Does EPA endorse or use models used outside of the United States? For example, the Mike Shee model or others, not proprietary model. Go ahead.
I would just say, and as has been stated earlier, EPA doesn't endorse models, especially not proprietary models. That doesn't mean that they can't be used. It just means that EPA isn't going to endorse a tool like that. I will say that there is, well, at least for me, a personal preference for open source models, just because I like to actually get into the model itself and do a little digging. But yeah, the simple answer is EPA doesn't endorse models, period. At least not commercial models at all.
Okay, thank you. I wanted to remind everyone that you can get a copy of the presentation in the downloads box on to the right of your screen. So if you are wondering whether you can get a copy of the presentation, you should be able to see a PDF version of the slides. And so if you're looking for any of the resources that have been mentioned, web pages and contact information, don't worry if you didn't write it down. It's all in the presentation, and you should be able to download it in the downloads box. How about a couple more questions? And I don't know if this is for Tame or for Jason, but what is an example of when you would use a statistical model over a mechanistic one? And would a statistical model ever be appropriate if you want to understand a future condition? No softballs here.
I'm willing to take it, but Jason, do you want to go?
Go ahead, Tame.
Okay. I'm sorry. So, just so I remember, so when would a statistical model be more appropriate than a mechanistic model?
Yeah. When would you use one over a mechanistic model?
Well, okay. So a statistical model, there's nothing inherently more or less wrong with using a statistical model over a mechanistic model. If the question you're trying to answer is appropriate. A mechanistic model, you're trying to assess all the different things that happen to your pollutant or in dealing with your environment, that could possibly happen, and really get a good handle on those interactions. In a statistical model, you're essentially saying, as something like this, as ambient temperature goes up, the water temperature goes up, and you just kind of draw that line, and it's a statistical relationship. that doesn't mean that it's any less, realistic. It does happen that way. And an example of a decent, what I would consider, a mostly statistical model, because most models have some level of combination of the two. There are some statistics involved, as well as the mechanistic way of representing a variable. But bathtub, for example, is primarily a statistical model, and it has its application primarily in the area where it was developed. It does a pretty decent job of looking at chlorophyll A, as well as phosphorus and nitrogen. It does a pretty good job in kind of small lakes in the southeast, and it can be extrapolated to a degree, but you wouldn't want to take that and then try to do a lake somewhere in northern Canada, just because the equations that the model is based on aren't representative of that area. That doesn't mean it might not be right one, at least, twice a day, but it wasn't developed with that data set in mind. So, so I guess so when would you pick one over? If you're comfortable with the data that was used to develop the model, for example, if someone wanted to use bathtub and the type of lake being modeled kind of fell into those criterion, I'd be okay with it. At the same time, I wouldn't feel nearly as comfortable trying to apply bathtub to a situation that was just really outside of the norm from which the data that was used to derive the model relationships was developed.
Okay, thank you. Let's see, a few more questions from the audience. Here's one that's probably will be a pretty popular one. Where does one go for funding to develop a model?
Well, that is a great question. Yeah, there are dwindling resources everywhere in all agencies across the U.S. It's one of the reasons we've come together as this group, and we all recognize that there's dwindling funds as well. And that being said, there are 319 grants out there. There's a variety of grants. There may be local grants. There may be money from your state legislature, just money allocated from your agency. And I guess I would say, like any other tool that you would use in solving a water quality problem, if I told your agency that you couldn't use, say, Microsoft Office anymore, that would be a real problem. And I think if you told your agency, well, I can't use water quality models anymore, that might be a problem. So maybe the point is I look at models as a tool, just like ArcGIS, just like Microsoft Word, just like your phone in your office, and it should be a tool that's available to you in your toolbox, whether that's in the form of funding to pay a contractor or someone to do the model, or whether you hire a staff person to do it yourself, or some combination of both is left up to you, of course.
And you don't have $1 million to give everyone for all of their modeling studies? That's not what people wanted to hear, I think.
No, we do not.
Okay, well, let me, as we've been asking and answering these questions, you may have looked at the current slide that's showing on your screen. And as we mentioned at the beginning of the webinar, there is a certificate that's available, a certificate of participation that's available. And you can download the certificate by copying the link that you see on this slide, the top link, the FTP site. You should not need a login or password for this. Copy and paste this into your browser, and you should be able to download the certificate that is customizable for yourself and whoever is watching or attending the webcast with you today. And also the second link on the slide that we're looking at now is where you will be able to find information about the future webinars that the work group is going to be hosting, as well as where you'll be able to find the archive of today's webcast. So you can check back at that web page periodically for updates. I believe that we will have the ability to, since all of you have registered, we have your emails and we can notify you when the archive is available. So please do check back periodically because we are hoping to have that archive available in 2 to 3 weeks. Finally, there will be a survey that when we are finished today that will be on your screen, and we do encourage everyone to fill that out as best as possible because we would love to hear how we did, and there will be the ability for you to weigh in on future topics because, as Jason mentioned in his presentation, we have the next 5 webinars somewhat mapped out, but not entirely, and we do intend to take into account your comments and suggestions and very much welcome your feedback. So with that reminder, I think we have time for a few more questions. So I will go ahead and dive right back in. How about, let me just find one here. What kind of models go together? And if you want to use 2 or more models in one watershed, I guess this question is referring to maybe linking models together. Jason, you talked about linking different models together in your section. Perhaps watershed models and receiving water models, and which ones you like to put together.
Region 10. Either of you like to take that?
Well, I guess if Ben is willing to pass up, I can take that one.
Maybe folks are getting tired of Tame and they want to hear me. Hello, everybody.
You know what, Ben? Feel free.
I've butted in.
Go for it.
Just a simple example of one we're working on out here right now. We've combined the HSF model, the watershed model, with the Qual2 KW water body model or receiving water model. And we're doing that because we want to look at stormwater effects on a local creek. And we're looking at a variety of pollutants, including temperature and dissolved oxygen. But that's an example of a linked model. 2 models that are linked together. I should note that sometimes one model is used, the output is then evaluated, and there's great care in taking that output and inputting it into the next model. So you deal with the question that I think somebody brought up earlier of when you link these models, do you create more uncertainty? So it's something to pay close attention to.
Thanks, Ben. We're glad you're on today. I have another great question here. Are there costs associated with maintaining models, or are they free to use and maintain long term?
Well, I would say that it depends on which model you're referring to. There are several models out there that are free to the public and that are developed, essentially without any cost associated, and they will continue to be developed until such time that the developer decides to change gears. But there are also lots of models out there that are that are not free, that have costs associated, and several that have licensing agreements involved that expire on an annual basis. So The answer is there are some that are free and some that aren't.
Very good. Okay. And we're getting down to the end of our time here, so I think let's pick one more question. And while folks are filling in the survey, how about here's a question about bacteria simulations, and what are the best models for those? E. coli, fecal coliform.
I guess I would say, thinking about bacteria and how it works, bacteria are very highly variable. They can be highly variable even by the minute or by the hour. So if you were choosing a model for a pollutant like that and you were interested in knowing how the bacteria change over those very short time frames, then you would want to choose a model that has the ability to do such a thing. So I'm not going to, well, I guess I could recommend a few specific models, something, a dynamic model, a mechanistic model with a very short time step, something like HSPF would be an example. So this is a great situation, though, again, harping on knowing what your water quality problem is and how you want to solve it, where you certainly wouldn't pick a model that has, a monthly time frame, or you wouldn't pick a model that applies at a very large scale if you want to know how your bacteria change for a specific beach or something like that, where you need to know site-specific results. So again, know your problem, know your model, use the resources that are out there to pick the model that has a short time frame and the ability to simulate bacteria.
And with that, thank you, Jason, and thank you, Tane. Thank you, of course, to everyone who joined us. We would like to conclude today's webcast. I will note really quickly before we sign off at the end, the next training session or the next webcast is scheduled for April 23rd, and we will be sending out registration information to everyone who's registered today for that one, and we look forward to you joining us again for that and the future webinars. Thanks again for joining us.